Hello, in this video we'll be looking at velocity time graphs. Now we'll start off by drawing the axes. So we will have velocity v in meters, let's call it seconds to the minus 1, and meters per second, and against time in seconds. Okay, now let's start with a situation where we're traveling from a point A to point B, and the velocity will be in the direction AB, as in positive in that direction. Okay, so let's start off, and there's a chap here, and he starts to run. Let's have him running. We start him running from 0 meters per second up to a certain velocity. So what we'll have, it starts off at 0 here, and he runs. Okay, and his velocity increases until he reaches, say, 6 meters per second. Okay, and let's say that takes him 2 seconds. Now, the gradient will be equal to the acceleration A, because the acceleration is equal to the rate of change of velocity. So that's a change in velocity over the change in time, and that can also be written as dv dt. Okay. So what will the gradient be? Well, the gradient is equal to 6 divided by 2. It's equals 3 meters second to the minus 2. So the acceleration is constant, it doesn't change, and that's the first part of his journey. Now, what he does next is he gets to 6 meters per second, and he decides to stop accelerating, and he'll just cruise along for a bit. So he carries on cruising at 6 meters per second, so therefore constant velocity. Okay, there is no acceleration, and he does that for another 4 seconds. So that'll be here, that'll be 6 there. Okay, and then he decides, after doing that for a while, he's going to slow down quite quickly and stop, and therefore it'll take him just 1 second to do the next part of the journey. So at this stage here, so let's call that O, P, Q and R. So O to P, that's a constant acceleration of 3 meters second to the minus 2. P to Q, the acceleration equals 0, and its constant velocity is 6 meters per second. And then Q to R, well, it's a negative gradient, so therefore it's going to be a negative acceleration. So therefore now the gradient here, the gradient is equal to the change in y. So the change in y is 6 divided by the change in the x direction is just 1 second. So the gradient is, in fact, it's negative. So it's minus 6 meters second to the minus 2. So he decelerates rather quickly and comes to a stop. Perhaps he ran into a tree or something. Okay, so now he finds, what else can we find out about that journey? So I'll rub out the bits and pieces we don't need for now. So what else do we know about the journey? Well, we do know something. Now, the area under the graph represents something known as the displacement, as we have covered before. Displacement, that is if you like, the distance travelled from A in the direction of B is the displacement. So what is the displacement? Well, it's the area, equals the area under graph, if you like. And in this case here, that will be, so we've got a triangle, rectangle, triangle. So the area of that will be half base times the height, so that's 2 times 6 divided by 2, so that's 6 plus, this is 6 there, times 4 plus 24, and here we've got 6 times 1 divided by 2, so that's plus 3. So therefore the total area under there is equal to 9 plus 24, which gives you 33 meters. So in his entire journey he's covered 33 meters. Now the final example we're going to look at is we're going to model somebody throwing an object up vertically into the air. So there's somebody and they throw something here up vertically up into the air, and of course eventually it will stop. Now often in physics we're going to assume that when it starts off here there's no acceleration, so we're going to assume the initial velocity is going to be, say, let's say 20 meters per second. Now eventually, as it gets the top as high as it can in this direction here, it's going to stop, and the velocity here at the very top is going to be 0 meters per second. Now the acceleration acting upon it will in fact be gravity acting down, which is g, and for now we're going to call that 10 meters seconds to the minus 2 acting in that direction. So what will it look like? So if we were to draw a graph of velocity against time for somebody throwing a ball in the air, and it starts at 20, okay, in fact that's velocity in meters per second, it's going to look like that. Now the gradient is going to be equal to, assuming velocity positive in that direction, so if we're having, this is our positive direction, therefore the acceleration will be a negative value, and therefore what we want, that's going to take us 2 seconds. So the acceleration A is going to be change in velocity, which is 20 divided by 2, and that's going to be negative, which is minus 10 meters second minus 2. So that's what it's going to look like. Now, what would happen if it throws it up in the air, and of course what comes up comes down. Now of course in this situation we are ignoring, we are in fact ignoring air resistance, so it's going to come down again. And what's in fact going to happen is, because acceleration is still going to be 10, but a negative 10, it's going to continue like that. So if it starts at 20 there, it's going to finish at minus 20 there, and that is going to take us 4 seconds. And again, the gradient will be the same as minus 10. So that's the situation modelled here. It goes throwing the ball up and down. It'll be a straight line like that.